Welcome, everyone. So glad to have you with us today for our brown bagger with Roger Wiens, and we're going to explore that. My name is John Wood. I am the president of the council and the executive director of the ASA, and so glad to have you with us. These brown bagger events are something that we have started in this year of COVID. It's an opportunity for us to take some of these really important talks that are made during the annual meetings in particular and at other places, and to bring those forward again, and then to take a talk that we've heard, so it's a vintage piece. You're going to hear something that has been given before, but also then to add live to the speaker and get a time for question and answer. So today we've cut the tape down. You know, about 45 minutes is how we'll proceed with that of a previous talk that Roger gave to the Michigan chapter, the West Michigan chapter of the ASA, and then he's going to come on live for a few minutes and bring us an update and do that live, and then we'll have a Q&A. We do have a chat function, and after the, I see Vicki has put a welcome in that, and you feel free, if you have questions that come to mind, to enter them into chat as we go along. I will scan those, and then we'll have about 10 or 15 minutes right at the end for a Q&A time. So that's how we're going to proceed. These are an opportunity for us to expand on previous talks and explore things that at our annual meetings, in our local chapter events, we don't get a chance to, so we get a wider audience, and then we can get an expansion of thought. So Roger, welcome, and so glad to have you with us today. Before I introduce you, let me open with just a brief word of prayer. Give thanks to the Lord for what we're doing. Father, we do thank you for the American Scientific Affiliation, for the women and men who have conceived of this organization and kept it going for some 80 years. We've watched some remarkable things happen, and we are so pleased to be part of that. So many involved professionally in the sciences in various ways. And now we have a chance to reflect on a particular part, a glory of your creation, to stretch our minds and our machines to another place in the solar system. And Roger's going to speak to us about that, and we ask you to bless him as he comes to us in our conversations together today. In Jesus' name, amen. Well, good to be with you. And Roger's background, he is at the Los Alamos National Laboratory, where he's the principal investigator of SuperCam. It sounds more like a Hollywood title, Roger. You're investigator of SuperCams, but he actually is what it is. The creator of these remarkable instruments that extend our capacity to know and to understand. And you have likely seen his achievements. He has traveled literally the world in all of the major laboratories and places where NASA research is being conducted and people are cooperating. And I understand the Perseverance is also cooperative. There's international participation in that project. So it's quite remarkable career that he has had, and we welcome him here today. And now we're going to hear the talk that he gave in the West Michigan chapter not too long ago. Becky?
So let's start with the question, what is our universe? And how does Mars and our exploration of Mars fit into that? Why are we doing this? So if we look back in time, here's one of the first maps from this era when the New Worlds had been discovered. And so all 7 continents are there. But if you look for Australia, it's hardly a continent there. So anyway, going further along, now we can start in the 17th century to start to realize Earth is part of a solar system. And so this was another huge revolution in thought that they were not just around Earth, but that they were around planets, around our sun. And so once again, people started thinking about what would be the kind of creatures that would live on these other round planets that are orbiting our sun. And so there's a lot of speculation about that, and we'll get back to that in just a little bit. But first, just looking into our stellar neighborhood, the parallaxes were measured in the 20th century, and so you can see we have only 33 stars within about 12.5 light years. But if we go back about 20 times as far, then we have 250,000 stars. That's about the reach, as I understand it, of SETI, assuming sort of typical radio signal strengths like the Earth puts out now. And so there's, of course, a huge amount of the universe that's beyond that. And so that leaves a lot that is not being listened to or thought about that much. So we have 200 billion stars in our Milky Way galaxy. And then to make us look and feel really small, we have some 100 billion galaxies in the known universe. And this is, well, the lines in this are actually indicating modes of or directions of motion. And do we really understand this universe yet? I would say no, not at all. And so it's, you know, the 21st century could be just as interesting as the 20th in terms of all the discoveries that might be made. And so I'm really excited about that. So just to think a little bit about Christian thought about this, C.S. Lewis in his 1958 essay, Religion and Rocketry, speculates about life elsewhere in the universe. And we also know from some of his other works, his fiction works, that he was really delving into the question of, if there are other worlds, did God visit them with his son, perhaps, like he did our world? And you know, I think his fiction is so creative that it just leaves us really thinking about what God might be doing or have done with part of the rest of our universe that we just don't know about yet. And so that this leaves me really curious about the universe and about God. But thinking about the possibility of life elsewhere, Frank Drake, at one of the first SETI meetings in 1961, put up this, penciled this equation. And so this is a number of factors that have to go into sort of an estimate of the number of civilizations whose electromagnetic or radio emissions we could detect. And the problem, of course, with this equation, it's been known for a long time, but the problem is that most of the factors are really highly uncertain. And so that leaves us with a lot of uncertainty on this whole thing, of course. Now, jumping ahead a lot in my talk, so I'm skipping a whole bunch, but Mars turns out to be within the habitable zone of our solar system. And so you can see that in the image in the lower left. Habitable zones can actually differ quite a lot depending on the amount of volatiles on a planet and various other things. And in fact, if you think about, if you know something about astrophysics, a main sequence star will start out with much lower luminosity. And so it's well possible, as we actually just talked a little bit before the talk, that Venus might have been in the habitable zone early in our solar system's history. But Mars is certainly there, and it's something we can explore. And just over the last 10 years, we've really understood that Mars was quite habitable some time ago. And it had these lakes, rivers, and probably oceans, and may have been as habitable as Earth at that point in time. And so to look at Frank Drake's equation with Mars in view, we're really looking at one of these highly uncertain factors when we look and try to understand if there was life on Mars. And that is a fraction of suitable planets on which life actually develops, or we can say is created, or it has the potential to develop based on what God has done. So that's pretty cool. And so we're trying to understand a lot more of our universe this way. Now, you could almost say that Mars is too close to Earth. In fact, right now, we're coming up on the close approach of Mars within the next several weeks to Earth. And if you go out late at night, you'll see Mars, which will be at its zenith right around midnight, very bright. And In fact, almost visible as a small sphere to the human eye. And so it gets so close that at times there probably has been transport of life, possibly from Earth to Mars at some times in the past. We know that because there's over 150 Mars rocks that we have found on Earth, and I actually made my PhD work studying one of these. But you can imagine that if there's that many Mars rocks that have come to Earth, the reverse could have happened, and we could have certainly seeded Mars with bacteria over time. So why we don't find more life on Earth is a very interesting question, both from a sort of independent origin of life kind of idea, and then also from sending it there from Earth. Now the question can come up: have we found life on Mars already? And it turns out that in 1996, Dave McKay authored a paper on carbonate structures that are found in one of these Martian meteorites that were supposedly resembling bacteria. I mean, on this photomicrograph from SEM that you see on the left, you can see these little things that look like they might possibly be living organisms. But it turns out that the magnification is turned up too high on this microscope. They're actually too small. They're almost a factor of 10 too small to be even RNA, which is the smallest building block of life on Earth, or at least terrestrial RNA. So it doesn't seem like these are evidence of life, but it certainly caused quite a stir. So anyway, during coming back kind of to our historical tour that we had earlier, starting about 150 years ago, we had first the Italian Giovanni Schiaparelli, and then later Percival Lowell in the US, really trying to popularize this idea that there were canals on Mars. I spent part of my childhood looking at Mars through a telescope, and with atmospheric turbulence, you actually start to see things that look like these lines on the Mars globe. You look at it during close approach, but in fact, they're optical illusions. But their idea was that this was, they knew that the atmosphere of Mars was thin, that it was too far from the sun to have a lot of energy. And so they were suggesting that this was a dying civilization that was trying to keep water going on this cold planet. And it wasn't until the 1960s that they were really completely proven wrong, even though telescopic observations with photographs showed that this wasn't really the case in the earlier 20th century. But okay, so by the oh yeah, and I forgot that Edgar Rice Burroughs certainly capitalized on this, and one really great thing we got out of this is science fiction. So that whole genre popped up after Schiaparelli and his Flagstaff colleagues. So that was kind of fun for many of us. Anyway, in the 1960s, we started out with the flyby missions with Mariner 4, and it turns out that these flyby missions only generally could see one side of Mars because they flew by so rapidly, and we were a bit unlucky because they saw mostly heavily cratered regions of Mars, and it wasn't really until the orbiter arrived, Mariner 9, in 1971, that we started to see this really great evidence that there had been water on Mars. And yet, because of the thin atmosphere and the sort of modeling work that was done looking to the past on Mars, it was argued that this could not be water that had created these canyons. And I remember even at scientific conferences in the 1980s and 90s that was the case. Now in 1976, we had two twin landers that were the first to land on Mars, the Viking landers. And in fact, one of the really interesting anecdotes is that President Gerald Ford called up Mr. Martin, the project manager of this project at JPL, and he asked Mr. Martin, he said, "Would you see anything if it moved on the surface of Mars?" Suggesting we were still looking for a mouse or something else that might possibly be living on this barren surface. But there were also organic tests on the Viking landers. There was a couple that came up a bit equivocal, but most really, they showed that there was really no organics that were observed with these experiments. And some of the equivocal results were based on some chemistry that was not really known at that time. And so the whole idea that there was life on Mars kind of went away, and it lay dormant for a number of years, and until the era of the Mars rovers. And that started with the Sojourner rover in 1997, this tiny little rover, and that was followed by the twin Spirit and Opportunity rovers in 2004. They had only 11 kilograms of payload instruments. And then in 2012, we got the Curiosity rover on the surface of Mars. And this had something like 160 pounds of payload. So it was really a huge change in the ability for us to start really seriously exploring the red planet with sophisticated instruments. And so that was a great time. And so a lot of what we know, some of what we know stretched from these earlier rovers, but again, the organic searches and so on really stem from the era of the Curiosity rover. And its goals were, for the first time since Viking, to assess Mars' biological potential, as well as to look at the geology of a landing region, study past habitability, and characterize human hazards. And when we think about Mars, going back to looking for life or thinking about life, one of the issues with Mars is that it is an old planet. When we look at the Earth is tectonically active. Many of the surfaces of Earth are geologically young relative to the age of our solar system. And but Mars is more like the asteroids and some of the other objects of the solar system. Its surface is generally very ancient, and so the globe that you see in the top is color-coded by the three eras or periods that we have in Mars history. So the one on the left is Noachian. It was characterized by valley network, and it appeared to have been rather warm and wet, possibly. There was there were all these channels that were made and a lot of sediments. So that's the purple part in the southern hemisphere. And then you had the yellow, which is Hesperian. And then by 2.7 or 2.8 billion years ago, you had the Amazonian. But if you look at the material that was emplaced on the surface of Mars since that 2.6 billion years, it was only the basically some volcanic highlands and a bit of polar area. And so if it's almost like going back in time billions of years by going to the Mars surface. Because if we look at Earth's equivalent history, the era from which most of Mars's surface still exists is the earliest time that life was actually confirmed on the Earth. And so we're really going very, very far back in time, especially biologically on the Earth. And so let's look at that just a little bit. The terrestrial biological timeline, all of the fossils that we know of are all from the very far right side of this diagram. They're just from the last 500 million years. This is 0.5 right here on the, if I can get my mouse over there. And so you can see that arrow that says first familiar fossils. And so all of this time before that, we don't see any fossils, and people have always wondered what was happening before the Cambrian explosion. And it's because there really existed essentially organisms that were mostly consisting of single-celled creatures. And and in fact, if we look at the Mars time period when Mars was geologically active, that's way back before there was atmospheric oxygen on the Earth, before there was photosynthesis. And so only effectively rock-eating bacteria was living on the Earth. In fact, I like to show this picture. It's the tree of life on Earth, and just showing some representation of all the species. And we have to go back to extremely primitive material organisms to go back in time that far on the Earth's equivalent organisms. And another thing is that if we want to look at cousins of early life on Earth, we can find that in hot springs and deep sea vents. If we want to actually find fossils of the single-celled organism stemming from that time, we don't actually see them. The earliest material that we can actually see that looks like organisms is about 2 billion years old. Before that, the stuff just didn't seem to have stuck around or survived. Remember that the Earth has tectonic action and it has metamorphism as well. So if you have material that's actually survived near the surface of the Earth, a lot of times it's been not just on the surface, but somewhat below the surface, and it's been metamorphosed, heated up, and cooked. And so we just, and the organic material, of course, if you get that above 170 degrees C or something around there, it doesn't stay in its same form. And so we'll find kerogen in some of these early life forms, but not actual, or we'll find carbon, but not actual organic forms or molecules. But what we do find from the ancient Earth are actual structures that the organisms made. And so the one that we find in abundance, that we still find actually happening today, are stromatolites. And so there are organisms that will create stickiness, microbial mats. And that sticky property is something that caused sediments to not lie flat on lake beds and so on, but rather actually to poke up in domes and cones. And so we'll find these domical or conical shapes in some of the very ancient rocks. And that is the evidence that we have of some of the most ancient life on Earth. And I actually had the privilege at this time last year to be in the Northwest Australian area called the Pilbara and actually see some of these firsthand. And that's probably the place where they are preserved the best on all of the Earth. And the idea was that a few of us should go there so that we would know what we were looking for on Mars. So we'll see if we find anything like that. Another idea for Martian life would be if we could possibly find biominerals, organic molecules, or isotope ratios that would tell us something about that. And then on the right, you can see the stromatolites. On the top part is the ancient stromatolites, and modern stromatolites that are still alive or still being produced in a wet environment are actually down in this lower picture here. So when we think about, as well, this is another kind of idea that maybe we can find things that are sort of doubtful, but sort of hinting at this life. And so that would be these biofabrics that we've just talked about, these stromatolites. But more significant is if we could actually measure chirality of, say, amino acids or something like that on Mars. As many of you know, that all of the amino acids that we have that are produced on Earth from living organisms have a single-handedness, not their mirror image. And so that is based on the fact that life makes cotton. And so there's that. But we haven't gotten to that level of sophistication on Mars, and I'll just tell you where we're at. So the instrument that has actually done sort of the most of the work of the last 8 years on Mars is got a really simple name called SAM, Sample Analysis on Mars. They didn't get creative with the name, but it's this 40-kilogram piece of equipment that combines a large laboratory into this small package. It has umpteen valves in there. It has a vacuum pump. It has a gas chromatograph with a number of GC columns that you can see in the lower right there. And these are micro columns. It has a quadrupole mass spectrometer and a tunable laser spectrometer as well. And so this is the instrument that does organic molecules. It studies atmospheric gases and chemical compounds and isotopes. So I'll refer to its results as we go through this talk a little bit. And then I have to tell you about my favorite instrument on the Curiosity rover as well, which is ChemCam. That's the one that we sort of invented, and I led the proposal for this way back in 2004. NASA liked it and said this is a great idea for studying chemistry around the rover, and so it got selected. So it's an idea where we take a pulsed laser, and that laser pulse has the instantaneous power to light 1 million light bulbs, but it's only 4 nanoseconds long, so it doesn't take much overall energy from the rover. And we focus that down to a spot the size of a pinhead. It actually creates a plasma with all that energy, ablating material off of rocks or soils on Mars. And then we look at that plasma with a spectrograph, and a telescope and a spectrograph, and we get the atomic emission spectrum of the material that we just ablated. And so that's how ChemCam works. It's a technique called LIBS. And so I think I have a small video here if it works on your Zoom. So first of all, this part is just an animation showing it's a point, focus, and shoot technique. And then you'll see the two parts of the instrument. So this is a spectrometer part. It's a sensing part. It has electronics down here. And then spectrometers, they get their light. Actually, this sits in the body of the rover. And we get our light from a long optical fiber from the mast. Here's the mast unit. The laser is on the left, that cylinder. And then this is the telescope that projects the laser light, and then it collects the light that we get back from the target. And so we're doing a little demonstration here in Los Alamos for you, and we're going to shoot at a nice big iron pyrite target a few meters away. And you won't see the laser beam because it is invisible to our eyes, but you'll see the little flashes of plasma. And there you go. And we'll do it one more time here. And so you can see that this is visibly bright. And so we can do this out to about 25 feet away from the rover. And so we've done that. We've actually made over 800,000 laser shots, 800,000 spectra on Mars, and done a lot of chemistry. This is a time-lapse video that we made with a camera that actually sees through the ChemCam telescope. And we took a picture after every laser shot. And did about 100 laser shots into a soil on Mars. We do it long enough after the laser shot that you don't see the plasma. You're just seeing the effect of that laser beam making a small hole in the soil on a little bit of a slope. And so you can see the soil falling back into the hole, and you can see the material that spirals or that shoots out of the hole landing down slope from that hole. And it turns out we use this to discover that Mars soil actually has water in it. It's fairly hydrated. It's in fact as rich in water as, say, a soil in southern New Mexico in the summertime, which isn't bad. It's about 2 to 308% water, which is, like I said, really good for a planet that has a very thin atmosphere, only 1% as thick as the Earth's, and seems to be desiccated otherwise. So something in the soil has really tenaciously held on to water. So part of our goal with this rover was to determine if Mars really was habitable back in time. Remember, there were people that thought that water never survived long on the surface of Mars. So we went to one of the lowest places in this part of Mars. It was called Gale crater, and we went into this low area of the crater that's indicated by the red area down here and the stars where we landed. But before we landed, we knew that there was a valley and a channel that had gone down there now. So the blue is just colored in to show you the low parts of the contour, locally low, of the contour map. And then there was a debris area down at the bottom that we could see from the satellite images. And so we knew we were going someplace that might have been a lake and certainly looked like it had water that once flowed into it. But like I said, there were a lot of skeptics, so we're going to see what we found. Well, we started along and we started to find conglomerates. And for any of you geologists, you know that conglomerates are rocks that are basically river rocks that end up getting cemented together on the bank of a river based on some saturation of silica or whatever else it is that then precipitates between the rocks and just starts to cement them together. And you know that because there are a whole bunch of colors of rocks, rounded rocks, that are all stuck together. Normally, if you have an original rock outcrop, they would all look the same. So and I like this one in particular because it has this nice feldspar-rich clast right in the middle. But it's great, and we started seeing these things all over and showing that there had been rivers flowing there on Mars for long periods of time, long enough to round the rocks and long enough to make these conglomerates. We also saw center-dipping sandstone beds, center-dipping towards the center of the crater. And you can see that these rocks actually have quite a bit of layering here, some coarse-grained layers, some fine-grained layers. And that's exactly what you would expect to find in a delta area, river delta, kind of below the level of the water. So if you were to go look at the Mississippi River Delta, it's creating this right now down in the Gulf. And this and the conglomerate started to put us into a picture where we found, first of all, the river material, then we found the deltaic deposits, and we went about 5 miles over that, and then we started finding lake deposits. And these lake deposits were, we started driving onto a hill or a slope where these lake deposits had long afterward been eroded down, and we could actually drive up and sort of count these lake deposits, figuratively counting them. And we went up over 1,000 feet. So you can imagine as this lake was filling in, you would have all of these different layers that would be deposited one year after another. And so counting that all together, we had something on the order of 1 million layers, suggesting 1 million years for sort of a minimal time scale for this lake, assuming 1 year for each layer. And could have been a lot longer if the lake was a little bit intermittent and so on. We still haven't actually gotten to the top of this lake deposits in the 8 years that we've been roving with this rover, and we're still going. And so we sent this picture to the public just to say this was a very large lake. It's 90 miles diameter, basically, this crater, and that this was open water for a very long period of time, actually, with rivers going into it. So let's get back to the organics and the idea of whether there was life on Mars. So Sam also looks at methane. Methane's been a real enigma around Mars. There's a TGO, stands for Trace Gas Orbiter. It's a European satellite around Mars that's been studying, specifically looking for methane, and it doesn't see any. Well, the rover has seen some, and it has a seasonal variation to it. And so there are a lot of people that are scratching their heads and trying to understand why it is that right on the ground you seem to be able to sense methane, but getting from orbit you don't. And so they're really trying to address the atmospheric chemistry to try to understand what's going on to help us understand that. The fact is there seems to be a bit of methane released from the rocks or maybe from underground on Mars. There could be an abiotic way that is created through a process called serpentization of certain, it's a rock chemical process, or it could be biotic, so we don't know. So that leaves us with a lot of tantalizing details, but nothing completely, no silver bullets. So another aspect of this is sort of more circumstantial, and that is that when we started looking into Gale crater, we started seeing the oxidation state of the rocks is very much in disequilibrium. And so we will have magnetite right there with hematite, and those are two different oxidation states of iron and different minerals, and in ways that they shouldn't be together. So it's suggesting that you have quite a bit of disequilibrium there, which of course in some situations would suggest that there had been life, but there's other ways to explain these things as well, of course. I published a paper on some of the really strange spherules. This one on the left is almost on the size of a soccer ball sitting in the sediments of Mars. We hypothesized that it was due to a redox reaction that was then spreading through the wet sediments, because we do have terrestrial analogs from the Navajo Formation in the western U.S. But there's other things there. We had some really strange, very interesting shapes that we've seen. In fact, some of these here we see iron oxide that seems to have been co-precipitated with calcium sulfates right in this upper picture here. We saw these strange kind of stick-like figures that are also iron oxide as well. So very strange things happening with the oxidation of from groundwater on Mars. And in fact, in one place, not just iron, but we saw manganese that was deposited on a very flat rock. And so what we think has happened here is that manganese was in solution in groundwater, and that it hit an oxidation front, and manganese will precipitate out if there's a lot of oxygen. And so we actually shot through this with the laser on ChemCam, one of the other chemistry instruments. This layer was so thin that it actually just saw right through it. It's only a few tens of microns thick. And so this was also extremely interesting. There's a bunch of people that study manganese deposits in the early Earth. Very interesting subject. But structures. We did not see any stromatolite structures on Mars so far. And in fact, carbon abundances are quite low in the rocks. So that's sort of an interesting absence there. So I'm going to switch gears a little bit now, and we're going to talk about the Perseverance rover. And you'll see that, and so this is the rover that was actually announced back in 2012 after the landing of Curiosity, that NASA would pursue another rover. But Perseverance has just launched this year. Its goals are, in some senses, similar to Curiosity. It's going to explore a different area for geology, ancient habitability, seek signs of ancient life. We have different instruments on it. But then there's two of these goals right at the bottom that are very different. One is gather samples that could be returned to Earth by a future mission. And another is to demonstrate technology for future human or robotic exploration. So I'm going to tell you in the rest of this talk a little bit about Perseverance and what we're going to be doing over the next several years. Just a caricature of the two rovers shows you that they look very similar. On the outside, they hold different instruments, and so we were able to do different studies than we were able to on Curiosity. Unfortunately, we don't have anything equivalent to the SAM instrument, but we have different ways to look for organic molecules, as I'll show you in a minute. And then the big thing on Perseverance is that it's collecting samples that we hope to bring back to Earth at some time in the future. So that's what we're going to show. First of all, I'm kind of proud of this. This is the cover of our proposal for that rover. And so we submitted this in 2014. We wanted to basically show that we were going to do a ChemCam instrument on steroids. And so what we did is we were able to pack three different techniques into the same size instrument as we have on the Curiosity rover without actually adding any more mass or taking up any more space on the rover. And so that was thanks to some really great technical teams that we have both here in Los Alamos and in France, which, a country that we partnered with for this. And so we've added a remote Raman and time-resolved fluorescence and invisible and infrared spectroscopy as well. So I'm going to unpack a little bit of that for you in a few minutes, and I see we're getting close to being out of time. So SuperCam does the same LIBS technique, and you see that on the left with that flash that you already saw. But we then take a frequency doubler and make a green laser beam, and we do green laser Raman spectroscopy, and you can see that with that blinding green flash. So we do Raman spectroscopy, and we do this infrared spectroscopy. Those are both mineral techniques. And then my French colleagues had the gall to try to add something else, and so we've added a microphone onto SuperCam, and we can actually listen to the sounds on Mars as well. And that has some pretty good scientific applications that you can ask me about later. So we also got involved in an instrument called Sherlock, and that has the coolest acronym, and it also has the nicest picture because you can see Sherlock's shadow with his pipe and then his magnifying glass. And his magnifying glass is showing a clue, just like the detective, and that clue is organic molecules. And we built part of Sherlock here at Los Alamos, and then the rest of it was at JPL and at a laser lab in the Los Angeles area, and an imaging lab down in San Diego. And so the Sherlock instrument is really the instrument to look for organic materials, although SuperCam has some of that capability as well with its green laser. And so this is another Raman spectroscopy and fluorescence instrument. It uses ultraviolet laser, and there it has an imager that looks very closely at the surface. And so the wavelength band is shown in the lower left, or the lower part of this. The Raman spectra are shown in the very far UV, and then fluorescence is shown at longer wavelengths. One of the problems that Raman spectroscopy sometimes has is separation of it from fluorescence, which is a lot brighter signal. But by going very far into the ultraviolet, they can actually separate that easily. We do it with SuperCam by separating it time-wise, and we have an intensifier that is time-gated with a resolution of 10 nanoseconds. But you can see some of the detection of Sherlock is in subparts per million for some of the organics, and so we're really excited about that. It has very small spatial resolution. It's going to be looking at very small spots. And so here's a little bit of some of the spectra that have been taken on the ground of different organics to show what we hope to possibly find on Mars. And so we will see in time. And so actually applying this to something like a stromatolite, which we talked about earlier, the Sherlock instrument actually took some mapping images, and then there's also an instrument called Pixel that's on the arm of the rover as well, and that'll show elemental composition. And the idea is if we find the right place with some of these materials, and if there are organics, we can also characterize the chemistry around it. Then looking at human resource utilization and human spaceflight eventually, there is a tech demo of an oxygen production box, and that's called MOXIE, and it'll produce about 1/4 of the needs of one human while it's operating, and it has a catalyst bed that operates at 800 degrees C. And it's something like that. It's going to give a demonstration that we can produce oxygen out of the CO2 in Mars' atmosphere, but it would have to be scaled up a lot, of course, for a human mission. But it's going to be cool to see that working. Then something that everybody's interested in is the helicopter that JPL built as a tech demo. And so this is something that weighs basically under 5 pounds. It has a blade span of almost 4 feet. Almost 1.2 meters, and so it's just, but it has to have these huge blades because the Mars atmosphere is only 1% as thick as the Earth. And so the idea is that this thing is supposed to fly several times in the first month after landing, and then supposedly its mission will be done and the rover will go on and do its stuff. I have a hard time seeing this helicopter die unless it really has an accident, so we'll see what happens. I think all bets are off. We'll see what happens. So looking at the landing sites, Perseverance is going to go to a location about 17 degrees north of the equator off to the side of Sirius Major. This picture always looks upside down back from my times when I used to sketch Mars looking through a telescope. But we're going to Jezero crater. It's a much smaller crater than Gale crater, but it has a deltaic feature again. And so this delta, when it's imaged with spectra from orbit, you can see that it has a lot of purple in that delta, and that's a clay mineral called smectite. And so we're looking forward to studying that. We're going to look also at this yellow part. That's carbonate. Carbonates are quite rare on Mars from what we've seen so far. And that's something we don't understand. Why, with a carbon dioxide atmosphere and water that was open with open lakes on the surface of Mars, why did we have not very much carbonates on Mars? We have a lot on the Earth. And so that's one of the enigmas that I think we need to understand. This is almost in the form of a bathtub ring around the perimeter of this crater. And so we'll really want to see how this carbonate formed. And so there's a number of things that we're going to do in this crater as we go to explore it. Now, a lot of the attention of this rover is going to be on getting samples, and it's going to get samples by drilling and with a hollow drill, and so that we have drill cores. And that way we get samples from the surface of the rock, but also from inside of the rock. And so this drill is, I've got a real short video that shows, because there's a lot of mechanisms. Hopefully this works through Zoom. And this drill core gets brought back onto the rover. There is a whole system called the SCS, the Sample Caching System. It starts with this turret that brings the core encapsulated in a titanium tube down into this whole area. There's a second arm down there that then brings it to image the top, seal it, and then put it in storage. And it doesn't actually show all of those steps in this short video, but then it puts it in storage over on the left there. And then eventually those cores will be dropped onto the surface of Mars, and it's going to be left there for a future mission to bring it back to Earth. And so that mission is starting to get funding at JPL and other places to start to define that mission. And it's so first of all, here are 38 tubes that were being installed into the rover. This was, if you see the date on the left-hand side, this was in May of this year. at the height of COVID. This was in Florida, and this was one of the last things that got installed into the rover. Ultra sterile tubes, so that we didn't bring any organisms from Earth to Mars and think we found something when we get these back. And in fact, this is the belly of the rover, and I think the capsule is, the top part of the capsule is already on top of this rover. This is a wheel already folded up. The helicopter is already stuck there on the belly of the rover with the cover on it, and so it's all ready to go. And so this was just weeks from the launch. Now the caching strategy is one where we can drop those tubes individually, and so we'll probably drill a few, drop a few, and then maybe go to a more risky place. But if we were to get the rover stuck somewhere without dropping those samples, another mission could not really come by and get them out very easily. So we have to get them out of this rover and onto the ground. And so we'll do that maybe a couple of places. Stay tuned for how that works. And then there has to be two other missions that will happen. One with a Mars ascent vehicle, it's shown in the center here. Because of the lower gravity of Mars, it's only 38% of that of Earth, reduced atmosphere. A rocket about something that would fit in the room you're sitting in would really actually below the ceiling would get this into low Mars orbit. And so we need a way to get the samples into the cone of that rocket, get it mounted up and launched, and then it could go into low Mars orbit. There it would rendezvous with another mission that would ferry it back to the Earth with a capsule that would help it to get back through the atmosphere of the Earth and onto the ground. And so those other two missions are in the development stage now, or in the very early stages now, with hopes that would happen in the late 2020s. And that's the ultimate goal, in part because really studying organic materials is so challenging. And so we think that it would work so much better if we get the best samples back on Earth. Now, we've got at Los Alamos, where I'm working, and other places, we've got ideas that we would really like to explore for other places in the solar system. This envisions a lander on Jupiter's moon Europa. And so that was at one point hot to start developing. Well, that's been pushed back a fair amount now. So we started working on an instrument that would follow from ChemCam and SuperCam. We're going to call it Organicam. And so Organicam was going to be really looking for organic materials in an imaging mode. And we can do that using this fluorescence, time-resolved fluorescence that the Sherlock and SuperCam instrument use. But instead of a small spot mode, we would use it in a broadband mode. And so we started developing this instrument. There's the sort of the drawings of it on the bottom and the realized version of it on the top. And so we've got a prototype of that now that we're just starting to get in the lab to look at. So it's great to not only be involved in current missions, but think about the future. And so we've had a lot of fun with that. But for now, and I've got one or two more pictures on that. If we could make that thing lightweight enough, we would love to put it on another helicopter on Mars and go to lava tube caves on Mars. And some of those lava tubes have skylight openings, and that would a helicopter would be the best way to get down into one of those places, to get underground on Mars and be able to start looking for organic materials down there. So that's also just something that's pretty cool. The caves on Mars, some of them have very large openings, and you can see them from orbit, and so that would be a sort of a really cool dream in the future. But for right now, Perseverance has just launched, so it is now about 55 light seconds away from the Earth, and should get to Mars on February 18 of next year. And so we're really excited. We are praying for a safe landing. It's never a guaranteed thing. And so hopefully all will go well. I really want to thank you for your attention in this talk. And I think I'll leave it there, and we'll take questions after this. Thank you. Yeah, so I think I have about 5 minutes just to give an update, which isn't very long. But anyway, February 18 came, and thank God we had such a successful landing. And this time NASA put cameras both on the descent stage and looking up towards the sky crane as well. And so we have just amazing images of this rover being set down on another world, on Mars. And So if you scroll all the way up to the top of the chat, I put a link to the NASA videos. I decided not to try to show them here, given that we have only 5 minutes. But there it is, and you can see in this image, just before the rover touches the ground, there it is, with the on the lower part, you'll see the 3 cables that are actually holding the rover, and then you have the electronics feed or link on the near the back of the rover coming up to the stage that is lowering it to the surface. Just an amazing thing, and I really had my doubts. This worked one time back in 2012, but it was like, yeah, expecting it to work twice might be asking too much, but thank God it all worked. And we got such a smooth landing on Mars, and so we were so excited. So let me see if I can advance these slides. There we go. So again, here is the SuperCam instrument at Jet Propulsion Laboratory before it got shipped to Florida and launched. And so we are looking out of that window with this 4¼ inch telescope. The microphone is just right next to the telescope, just below and to the left there. And so we are using this instrument on Mars. And I don't have any pictures of the landing itself, but we landed right in that circle in Jezero Crater. We're a little ways away from that delta. We were hoping maybe we'd be very close to the delta, but we have about 1.5 miles to go, 2 kilometers, and a little bit of a circuitous route because some of the terrain's a little rough between us and the delta front. But that's going to be one of our major goals or destinations for the mission. Right now, the mission is just unpacking the helicopter. The cover that you saw earlier has been dropped off of the rover now. The helicopter is just hanging under the rover, and the rover is going to the helicopter drop-off point this week. The NASA just announced that the helicopter flights will happen no earlier than April 8th. So there's a few days of things that have to happen between now and then. In the meantime, the different instruments, the ARM instruments are not doing much yet. I think the Watson imager is still
Roger, you're muted.
Am I unmuted now?
You're all set now, Roger.
Okay. Did anyone hear anything I said so far?
Yes, just repeat your last sentence or two.
Okay, great. Yeah, I don't know what happened. Yeah, so I think I was just saying that the helicopter drop-off point is happening this week, and then the helicopter will get to its first flight no earlier than April 8th. In the meantime, the SuperCam instrument and the MassCam Z instrument, which is this zoom set of stereo imagers here, are working. The NavCam instruments are working as well. So we're getting those kinds of instrumentation so far. Let me see if I can advance this again. Okay, so SuperCam is supposed to do a lot of these different things. I already pointed that out, so I'm not going to go into this more. This is a talk that I just gave last week for a conference. But this shows some of our first pictures from SuperCam. And so we get this kind of round images, almost like you're looking through a spyglass. We're looking at the calibration target on the back of the rover here, and just to show, or just to demonstrate. But we have a little USAF target for imaging resolution here. And if we zoom in on that, we really think we have the highest resolution pictures from the rover itself. This is basically 1/3 of a millimeter, so a few hundredths of an inch, this red bar here. And we can see things, some of the bars here have a length of under 100 microns. So we're seeing specks of dust and so on that are approaching 50 microns. So we're really excited. We have started to train this camera at other things. And so here is our first target that we use for spectroscopy. The project started in a quadrangle that is named after Canyon de Chelly. We're naming all of our quadrangles after national parks around the world. And Canyon de Chelly in Arizona is actually a Navajo land. And so we started naming these targets after Navajo words. And this is the target Maz, which is actually the name of Mars in Navajo. And so this was the first target that we shot with the laser. You can see some of the mineral grains that are sort of weathered away by the wind here in this rock. And this is the first chemical spectrum that we got from Jezero Crater. And so I could try to point out a lot, but in 5 minutes, I don't have much time. Basically, this is, oh, and first of all, just to point out that SuperCam has a little better spectral resolution than ChemCam had, so that's nice. But basically, this is the spectrum of a basaltic composition. We can see all of the major elements from the alkalis to the iron and magnesium. And so you could say, well, it looks like it could be an igneous rock, but it has this kind of big hydrogen peak here. So that means that it's hydrated. It's probably got clay in there. And so probably it's igneous mineral grains or little tiny grains of sand that got moved and cemented into a sedimentary rock. So this was another target that we did, and we got our infrared spectrometer going on this one. And and we just looked at this, and again, it's consistent. This is very early results, but it's consistent with a hydrated sample that would tell us that there's some clay minerals in there. And so we're just starting to piece together some of the history of this. I pointed out a few things for the scientific crew last week. We also pulled out the Raman and luminescence, but all we've done with that technique so far is shoot at the targets at the back of the rover. So it's just showing that it's working here. We're getting a nice good Raman peak, so we're ready to go with the targets on Mars. But it's all happening fairly slowly for us as a helicopter kind of has dibs right now. This is the microphone. We got the first recordings of sound on Mars. The top plot just shows some wind sounds. And in the bottom plot shows us getting laser shots. And that's not, those spikes are not the laser itself. Those spikes are the sound of the little plasma that you saw right against the rock, hitting the rock. And so we're actually listening to the sound that it makes hitting the rock. And that's going to tell us about the hardness of the rock. So that's showing that that technique is working as well. By the way, you can go to the Jet Propulsion Laboratory NASA site at that, related to that link that I put in the very top of the chat, and find the sounds there as well, and you can download them and listen to them. And so just in summary, you know, SuperCam is working very well, and we're still in the early stages, but we're starting also to look at what kind of route would be taken to get to the Delta and a few other things. But I think I'll leave it at that because we just have the 5 minutes. And so I think the next thing is a Q&A. And by the way, it's great to listen to the talk and be able to answer questions as it was going. So anyway, thank you for your attention, and we'll take questions.
And thank you, Roger. This is a delight. If you've been monitoring the chat as I have, you know that Roger's been answering in real time, watching his talk and answering questions. I guess that answers one of the questions. Can we multitask? Apparently we can. That's a good thing. And there are two types of questions that I'm seeing in here. They're the more reflective and sort of philosophical questions that come in. And then there's these really interesting technical questions about the geotechnical and chemical and questions that are coming in. And so I want to answer one that you did talk about in the chat. That's the question that you started out with. We've got Mars rocks on Earth. And, you know, I think about my grandfather, you know, plowing the prairies. And I tell him, you know, well, some of those rocks might be Mars rocks, you know, down there. Oh, how can that be? And you gave an interesting answer. And then there was a question that came at the end. The answer is that there are objects that strike Mars or explosions of other kinds. I don't know if you meant volcanic or whatnot, that might eject things from the planet and then move through space. So the question that came to follow that is obvious. Would it be likely that some kind of living thing, some life form would survive on a rock? You want to comment on that?
Yeah, John. Yeah, I started my, let me grab a drink of water. Yeah. I started my scientific career with these meteorites that came from Mars. And initially, people, even the scientists, didn't believe we could get rocks off of a planet like Mars because of the impact that it would take and the shock level that the rocks would get in getting accelerated to escape velocity. But as they looked at the meteorites and we became convinced that they are from Mars, because they actually contain parts, their little glassy parts that capture the Mars atmosphere. And so we can see that. They've also been dated to much younger than the asteroids. And we now see that their elemental compositions match with some parts of Mars. So we know they're from Mars. And so actually what happened in this case, it is a case of where the theoretical modelers had a piece of data that they needed to fit, and they started to see that these meteorites can actually come from a planet as large as Mars. And then you look at the shock levels of the minerals there, and some minerals will change their form when they are shocked, just with a brief shock. And you can see that with explosions or with these impacts. And that's a field of study. And there's a number of people that are in it. And so we look at the shock level, and some of these rocks have a significant shock level, but then some places in the rock or some of the rocks have very low shock levels. And so somehow they were in a cloud of material that got accelerated off of the planet right at the edge of where the crater is now, and made it out into space with relatively little shock. So we're pretty sure that bacteria could make it in rocks like that and actually be ejected from Earth and get out into space. And so that's a pretty interesting kind of concept, that life created on Earth, starting on Earth, could end up on Mars, which passes within only 30 million miles of the Earth.
Mm-hmm. Mm-hmm. Yeah, that's very good. Thank you. That's helpful insight to fill in. I'm going to turn to an application question that has come in right at the beginning. Keith Shields asked this, and it's very good. He said, I love interplanetary research. Can you tell us how your Christian faith impacts the first of all, I think that just stop right there. How your Christian faith interacts with your disciplinary day-to-day work. And then we'll do the follow-up question, because this is the ethics of spending money. This is the age-old question about space exploration, right? And so we'll get your take on it. What are the ethics of spending money on interplanetary research while we might spend this money on some other earthly concern? So maybe that first question, talk a bit about what is it like to be a person of faith in a cutting-edge national research laboratory?
Yeah, I would say that exploration is a form of worship. We are studying God's creation. If you look at places in the Bible like Psalm 19, it talks about the expanse of the universe, speaking of the glory of God. And so I really take that seriously, and I say we are learning about God from his creation, and that has been the case throughout all of history. And we even see the mandate from God and from the Bible for us to explore, coming all the way from Genesis, where Adam was asked to name the animals. Okay, that is a form of exploration. You name things based on their characteristics. And so that's a kind of classification. And so we have that throughout the Bible, throughout theology as well. You just have to look in those places where it is brought out. So I see this as a way of understanding more about God than we would understand otherwise. And I believe it's important to not only study the Bible, but to study his creation. And that's, I think we really have a much more rounded view of God, of ourselves, of his creation in doing that. So now comes the question of how to spend money. And well, I don't have to make those decisions myself, in a sense, because the government has already made those decisions, and I am a very, very privileged recipient of that, to be able to do this. And I realize that I'm in this privileged position, and I really do want to share what we are learning and discovering to the public, because that is our job as public servants, to do that. Now you can ask the question, step back and say, well, should the government be spending money? Should we be electing or voting for officials who actually spend all that money? And so I think we can answer that in different ways. We're a diverse people when it comes to politics, and you know, I don't want to venture too far in there. I will say that this exploration is a form of worship, but there are many other priorities out there, of course, and so if we look into the Bible at what priorities were there, of course there are the priorities of helping the poor, of helping the sick, and of spreading the good news to all people. So those things are priorities as well. And so we have the difficulty of making those decisions when we go to the polls and so on. But anyway, I've just been very grateful for the position that I've been in, and thank God for that.
Thank you. That's an excellent response to that. You know, it is that some places I think it says the glory of God to conceal a matter is the glory of kings to search it out. So this science activity of searching out is really a remarkable kind of privilege, as you say. Christopher Southgate, has just released a book, 2019, theologically talking about the doxology, the glory of God. And I would say that the answer you gave fits into his thesis and his approach theologically. So I think as scientists, we stand on very firm ground that way. Nevertheless, there are choices to be made. And so thanks for helping us explore that. I'm going to give you an opportunity. This is a little risky because we've got so many people, but if someone wants to unmute and ask a question directly, if you don't, I have several others here written down. I'll give you a chance to. Well, you're thinking and not on the edge of your chair, so I'm going to step back in here. I really want to know if you found Mark Watney yet. I understand that he's farming potatoes there somewhere on the surface of Mars. And this is so that's the Martian movie from Hollywood. This interaction between Hollywood and it is a question about the theoretical side, where we get our ideas from. You want to talk to us just a little bit about what's influenced and sparked your imagination about Mars and keeps driving you and opening up new areas for you?
Oh yeah, well, thanks, John. I hope I answer this in the way you're wanting. But basically, what I get questions about, you know, how do we get people into STEM careers or things like that, or what's important to get into a career like this. And what I say is that I believe it's very important to be rounded, not just to study math and science and those kinds of things, but to study, to basically exercise both sides of your brain. We really work on creativity. And so science is driven by creativity, and we have to be creative individuals, especially as leaders in different science areas, to think about what to do next, about how to engage these different techniques. And so I really encourage people to go into different, to round themselves and to study philosophy, which can maybe ground science in some ways, theology, and all these other things. So let's see, I think I might have lost part of your question though, that was pertaining to potatoes. But I think one of those things is to try to think, you know, what could come next? What should we do next? This whole idea of human exploration is very tantalizing. I think it inspires us a lot. I don't know where that will go, but certainly getting samples back from Mars is an exciting prospect. And let's see where it does take us. But I think we do have a God-given mandate to explore. So I think that's something that's exciting.
It is. It certainly is. And, you know, you're so close to this research area. We focused on what the United States is doing and on our programs, but aware that it's a really international effort today. Could you say something about that? Because and the segue here is that if I understand correctly, the Chinese are very intent on actually putting a person on Mars, and the Mark Watney thing is, of course, imaginary at this point, but you see that on Netflix series and on movies. Clearly, this is in the mind of people. And I would say, I mean, the Chinese are working on how do you feed people going back and forth, touches on an area I happen to be in, edible insects and protein support. But in your case, what are these other countries doing? How do these, is there cooperation going on? Or is it just competition? How's it, just tell us about that.
Yeah, space is very political, actually, but it's because this is seen in the present day as being part of the prowess of a nation, just like in the 19th century, say, exploring for the Northwest Passage, or for the Arctic and Antarctic lands was something that was showing, somehow the prowess of a nation. So this Perseverance rover was actually the last of 3 missions to launch to Mars last July. We had our challenges with COVID and everything else, and thank God we made it. But the first out of the gate was actually the Emirates, which has now a satellite orbiting around Mars. And that was parts of it were built in other countries, of course, but they're using an operations center and over there in the Emirates. And then China launched its first Mars rover. That rover arrived at Mars in February, and it is orbiting Mars. They are waiting to deorbit it until sometime in May or June. And so we're waiting to see how that goes. Of course, we wish them good luck. In terms of collaboration, the U.S. Really works with space, mostly with its partners, the international partners, and so a lot of European collaboration. So the SuperCam instrument is a joint French-US instrument, actually. I speak with my French partner every day, literally, and usually, and even several times a day. And we hand off between operations in Toulouse, France, and here in the US. We're just getting it back. They did it the last several days. We're doing it now. And in the space station has helped keep some measure of relations with Russia going. But we're actually prohibited from collaborating with China right now. And so I don't know how long that'll be, but yeah, that's, it is something that's just the way it is right now, and we'll see how that continues. Of course, we want to use, when possible, use some of these things to encourage countries to adopt policies that are friendly to their own people as well as to other nations. And so we'll just see how that continues into the future. But it's also been very good from the international collaboration perspective. We have so many different people that are involved in Europe on these missions as well. So, yeah.
Thank you for that. That really sums things up, I think, in an interesting way. People of faith working at the edges of discovery across international boundaries with colleagues. What an opportunity for witness of the gospel by what we do, by who we are, and also then occasionally by what we have to say to folks. It's marvelous. This is a great opportunity. And thank you so much for bringing this to us today. There are other questions that are in the chat and have come along, but in interest of our time, I think we need to draw this to a close. Roger, thank you so much. I'm going to turn it back to Vicki Best and let her close the day. Vicki?
Thank you, John. And thank you so much, Roger. This was really terrific. I first met Roger and his wife, Gwen, at our 2016 annual meeting at Azusa Pacific when he was the plenary. And then, as mentioned, he presented at the West Michigan chapter launch, and this is where this recording came from. So it's a real privilege to hear from you again today, and it's great to see everyone, a packed house. I think we had over 150 people, and even some of our international members. I saw some folks from Norway and Italy, so great to see everybody. God is at work in the ASA and in many ways and amongst our members, and Roger is just one example of that. And it's really been an exciting time in our history. And we're mindful of the many ways that God really has blessed and transformed us this year in ways we could have never imagined. Meetings just like this one and our new normal, we've reached more people and engaged more chapters and raised more money than we have really in any year in our history. And we've got a number of upcoming events. I want to just share a few of them with you. Tonight at 7:00, the Boston, New Jersey, and Gordon student chapters are going to hear from ASA fellow Patricia Bocarsley. She's going to talk on marking 1 year into the COVID pandemic, the scientist Christians' responses of hope, concern, and gratitude. Our diving deeper discussions are off to a great start, the second Saturday of every month. Next one is on April 10th on vaccine hesitancy, Christian reasons and responses. So please join us for one of those. Our annual meeting planning team is in full swing, and a lot of people are wondering about our plans for this summer. So we will plan to make a public announcement next week. So stay tuned for that. And then we've got a number of chapters meeting primarily over Zoom. The CCU student chapter, DC, Montreal, Rocky Mountain. And what a great way to jump in on some of these meetings, again, with the Zoom platform. And you can find all these events on our events page on our website. We are 6 days away now from the end of our fiscal year on March 31st. And like I said, it's been a remarkable year and testing our endurance on all levels. But despite the challenges, it's really been quite remarkable. And right now we have less than $5,000 to raise to meet our annual fund goal. And in the midst of the pandemic, the ASA community really has responded overwhelmingly with many surprise gifts, first-time gifts, long-time supporter gifts. And we're just humbled and encouraged. And if you're in a position to help us with the first time or an additional gift to reach our goal, we'd certainly appreciate that. Our focus this year has been on three primary things: discernment, gratitude, and prayer. Discerning God's will for the ASA in these transitional and transformational times. Gratitude for our members around the globe and the ways God is using these times for his purposes and good, and incorporating prayer into all we are and what we do, from our daily lunch meetings to our weekly staff meetings to our bi-monthly prayer committee meetings, to name a few. And the ASA story written this year has been quite amazing, and we're just really grateful for all of you who are a big part of our story. So thank you very much. And as we close today, would you please bow with me in prayer? O most holy and righteous God, you're the ruler of the cosmos, giver of every good and perfect gift, including our inquisitive minds as scientists. You have been our dwelling place, Lord, through all generations. And we're deeply grateful to you this day and every day as we place our faith in you and you alone. We are trusting that you are using these challenging days for your transformative purposes. Please continue to bless Roger and his important work, and we ask you to give him effectiveness and wisdom and his service and vision to communicate the adventure of space exploration and encouraging others to pursue their dreams. As we celebrate the gift of scientific insight and wisdom, equip us to be the church around the world, living out our God-given callings, showing tangible expressions of our love for our neighbors. This Lenten season, Lord, we're reminded of your abounding love for us. You loved this world so much that you gave your one and only Son, that we might be called your children too. So, Father God, help us to live in the gladness and grace of Easter every day. Let us have hearts of thankfulness for your sacrifice. Give us eyes that look upon your grace and rejoice in your salvation. Help us to walk in that mighty grace and tell your good news to all the world. For all your glory, we pray these things. Go with us now in the powerful name of Jesus. Amen. Starting Monday, you will be receiving our Easter devotionals, and they will run all the way through Resurrection Sunday. So goodbye, everyone, and have a blessed Easter.